In this video, we'll identify the time and space complexity of common algorithms. If you haven't already, be sure to watch the Intro to Big O video first. We'll start with an algorithm that searches for a target element in an array. We loop through the array, and whenever we find the target, we return immediately. If the target doesn't exist, we return not found. This for loop could go through the entire array, so that is O of n. This if statement just does a comparison, so that's O of 1. And this return at the end also executes in O1 time. So to find the time complexity, we just add together the time complexities of the individual steps. And remember, in big O analysis, we only keep the most dominant term, so that simplifies to O of n. Now, you might wonder, does it matter that sometimes this for loop would not go through the entire array? Well, what if we have an input such as 1, 2, and 3, and our target is just 1? We return after the first iteration. Does that affect the time complexity? Well, sure, you could say that for this particular input, we have a time complexity of O1. But in the general case, we don't know where the target is in the array, so On is the tightest bound we can give. As for the space complexity, well, we are just keeping a pointer, so that is an O1 space complexity. In the next function, we are summing up half of the array. So we loop through the first half of the array and we get the sum. So these first two statements are just assignments. They run in O of 1 time. This for loop runs through half the array. So you could say it's On on 2, but in big O time complexity analysis, we drop the constants, so that simplifies to O of n. This return statement executes in O1 time. So adding that all up and dropping the non-dominant terms, we get O of n. As for the space complexity, well, again, we are just chucking a couple of pointers, so the space complexity is O of 1. In this function, we print out the pairs in an array using a nested loop. Let's go through an example. We'll use the array 0, 1, 2, and 3. Now, when I is equal to 0, j goes from 1 after I, so that's 1, all the way through to the end at n minus 1. Recall that in Python range statements, we always end at 1 before n here, so n minus 1. And that means we print out the pairs 0, 1, 0, 2, and 0, 3. When I is equal to 1, j goes from 2 to the end. And so we print out the pairs 1, 2, and 1, 3. Similarly, we also print out the last pair 2, 3. As for the time complexity, this assignment here is O of 1. The outer loop runs through the entire array, so that's O of n. And the inner loop runs for at most On on its longer run, even though the loop gets shorter and shorter as it progresses. The print statement here just is O of 1. So let's add that all together. We have O of 1 plus the outer loop O of n multiplied by the work in the inner loop O of n multiplied by that print statement there, O of 1. That is equal to O of 1 plus O of n squared. And we only keep the most dominant term, so that simplifies to O of n squared. But you might wonder, does it matter that the inner loop actually gets smaller and smaller as we go on? Can we just say it's On anyway? Well, let's go through and count the print statements more carefully, just using the general case with a length of n. Right, so we already have a start. And so when j goes from 1 to n minus 1, well, the print statement executes n minus 1 times. From 2 to n minus 1, well, the print statement executes n minus 2 times. Let's jump right to the end. When I is equal to n minus 2, well, j begins at n minus 1 and goes to n minus 1. So just executes one time And in the last iteration, when I is equal to n minus 1, well, j has to start at n, which is out of range, so the loop terminates. And what we need to do now is sum the numbers 1, 2, and all the way to n minus 2 plus n minus 1, because together this represents the number of times the print statement is called, and hence the amount of work that our algorithm is doing. And now let's notice that when we pair up the first and the last element, we get 1 plus n minus 1, which is equal to n. When we pair up the second element and the second last element, we get 2 plus n minus 2, which is equal to n. Can you see a pattern here? So we can couple up the terms from the start and the end, and they will all equal to n. And we just need to multiply by the number of pairs that we have. Well, how many pairs do we have? We have n minus 1 terms, so the number of pairs would be about half of that. And let's just approximate that to n over 2. So this won't be the exact number, but remember, in big O time analysis, we drop constant and non-dominant terms anyway. So being off by 1 is okay. N times n minus 2 is equal to n squared over 2. We have on squared over 2, and that simplifies to O of n squared because we drop the non-dominant term. So, all right, we get on squared, no matter whether we use a shortcut way of evaluation or we do it more in detail. Now, finally, let's just have a quick look at the space complexity. In this algorithm, we really are just creating a couple of pointers, so the space complexity is just O of 1. I want to really highlight the difference in computing time complexity for single and nested loops. When the loops come one after each other, we do A units of work, and then we do B units of work. So we add the time complexities. When the loops are nested, we do B units of work, A times each, and then we multiply the time complexities. Now let's look at a recursive algorithm. Fibonacci is a sequence of numbers starting with 1, 1, and then each subsequent term is generated by adding the two terms before it. So 1 plus 1 is equal to 2, 1 plus 2 is equal to 3, and so on. This algorithm generates the nth Fibonacci number using recursion. The base cases are n equals to 0 or 1, where we return n and end the recursion. Else, we add the term before and the term before that. As an example, let's draw out the recursion tree for fib 3. 3 isn't a base case, so we must recurse. 3 minus 1 is 2, so we call fib 2. 3 minus 2 is equal to 1, so we call fib 1. 2 is also not a base case, so we keep recurring. 2 minus 1 is equal to 1, so we call fib 1. 2 minus 2 is equal to 0, so we call fib 0. Fib 1 is a base case, and so we just return 1. Fib 0 is also a base case, and we return 0. Fib 2 returns the sum of the recursive parts. 1 plus 0 is equal to 1. Fib 1 is a base case, and we return 1. Fib 3 returns the sum of the recursive parts, and 1 plus 1 is equal to 2. And so fib 3 is equal to 2. We'll find the time complexity by drawing a more general recursion tree. We'll keep track of the level of recursion, the state of the tree, and the amount of work that we do. So at the first level of recursion, we just have one subproblem of size n. The amount of work we do, well, it's just one if statement here, so that is 1 unit of work. At the second level of recursion, Well, our subproblem splits into two subproblems of size n-1 and n-2. The amount of work we do is 2 units. At the third level of recursion, our subproblems split down again. So now we have a subproblem of n-1 and -1 again, which is equal to n-2. And then we have a subproblem of n-1 minus 2, which is equal to n-3. So similarly, for our subproblem of n-2, it splits into a subproblem of n-3 and n-4. In total, that is 4 units of work. Now let's try and draw a relationship between the level and the amount of work we do for some level in the middle here. We'll call it I. Let's rewrite these expressions a little. 1 is equal to 2 to the power of 0, which is also equal to 2 to the power of 1 minus 1. 2 is equal to 2 to the power of 1, which is equal to 2 squared minus 1. 4 is equal to 2 squared, which is equal to 2 cubed minus 1. And so at the ith level, the amount of work we'll do is 2 to the power of I minus 1. Now, at what level would our recursion finish? When will we hit the base cases of n equals to 0 or n equals to 1? Well, if we look at the left side of this recursion tree, notice that the size of the subproblem decreases by 1 for each level. So to get from n all the way down to 1 or 0, we need about n levels. And the amount of work we do at this final level would be 2 to the power of n minus 1. To find the time complexity, all we need to do is sum up the amount of work we do for each level. So that would be 2 to the power of 0 plus 2 to the power of 1, all the way up to 2 to the power of n minus 1. Here, I'm just going to use a formula for the sum of consecutive powers of 2, which would give us 2 to the power of n minus 1 at the end there. We won't go into a proof of this formula in this video. If you're interested, you're sure to find plenty of proofs online. With big O time analysis, we drop the constants, which gives us a time complexity of 2 to the power of n. What about the space complexity? It's tempting to say O1, right? Just looking at this, but we need to remember that is O1 for each level of recursion. And so our space complexity is O of 1 multiplied by the n levels of recursion, which gives us O of n. Now, how bad is 2 to the power of n time complexity anyway? Well, it's asymptotically slower than O of n and O(n) squared. There is an algorithm for Fibonacci that runs in O(n) time, and I did a benchmark of the two. The difference is quite drastic. This 2 to the n algorithm, it slows down so much such that by the time we're at 50 elements, it begins to be impractical to run, whereas the O(n) algorithm scales much better, and the slowdown here is much slower. We'll go through the O(n) algorithm in a future video. Well, that's it for today. Be sure to check out my channel for more.